So what has motivated us to give this talk? Well, I suggested it for a couple of reasons. One is that I'm seeing some really good work using the SBES model, which is the scale, stress blended eddy model here. And so that's one good reason to show it. Another reason is that I'm also seeing some very bad stuff around where there's a fixation with using LES without really understanding the requirements of LES. So that's really my part of the presentation. So if we just start on this front page, you can see that we've got a car, so a traditional aerodynamic simulation. All of our turbulence is coming from the wakes, from the spinning wheels, and we've got some very nice turbulent structures being captured there. But over much of the car body, we've got no separation. So we've actually got a RANS model there being used. And if we choose a suitable RANS model, that's going to do a better job than LES. Because to apply LES there, we're going to need a superfine grid. And if we don't do that, we will get things wrong. If we use a RANS model there where we know it works well, then we will get a good result. So let's quickly go through the introduction. So as I said, a brief introduction for me. Gary will be next, Kiao next, and then we'll try and have a Q&A. So just to set the scene, I mean, we've got three or so main turbulence approaches. People talk a lot about DNS, where you basically just solve the Navier-Stokes equations, very fine mesh, very small time scale, resolve everything, and none of us are going to do that because it's way too impractical. So large eddy simulation is the next step down, where we say, okay, let's do a spatial filtering of the Navier-Stokes equations, and let's resolve all the large scale eddies that carry all the energy, and then let's model the small structures where viscosity essentially is destroying the turbulence, turning it to heat, the kinetic energy to heat. And because that's happening at a small scale, we're really not so bothered about the detail of that. We can afford to skip over the detail there and still get a good model. RANS modeling is what 95% of people are still doing. And that's to take the Navier-Stokes equations, and we can average them in different ways. We can do a time average, or we can do an ensemble average. When we do that, we end up with some extra terms to be modeled in the equations called the Reynolds stresses. And most solutions that we get replace those Reynolds stresses with a couple of additional variables to close it, and typically K and epsilon or K and omega. The nice thing about RANS modeling is that turbulence is inherently 3D and transient, but for many flows, we can now get a steady state solution. So if you just take the simplest flow down a pipe, we cannot run that steady large eddy simulation. It has no sense to run a large eddy simulation in a steady state mode. But for RANS, we can, and we can get a meaningful solution from that. If we've got something else like, say, a backward-facing step where we know the flow is going to end up transient, we can just keep the transient term in the RANS equations and use something called URANS. We can do it, but we must do this stuff with extreme care and understand what we actually can resolve and what we can't resolve by doing that. So I'm going to talk about what I think is the seduction of LES. Okay, LES came about for doing large-scale weather forecasting, was the origin of this, and it's easy in theory because we just have a grid, we resolve it, and for many people it's just a case of switching it on. When you do that switch on, this is what you're trying to do. You're going to have to provide it with a subgrid scale model, which is going to dissipate the energy that we can't resolve. And so this is the famous picture where, as we go along the bottom, we're going from large eddies to small eddies, and up the vertical axis, we've got the energy contained in them. And the size of those large eddies, essentially where the peak is determined by your geometry. You've got larger scales, you can have larger scale vortices, and they get generated. And then there's this transfer of energy as they break up. And you can see there's an almost straight line there, which has got a -5/3 slope. And that comes out of the self-similarity of the turbulence there. And then we've got a grid limit marked there in red. And so if that's where our grid stops resolving, and typically we need, say, three cells across an eddy to resolve it as a minimum, then beneath that, we're going to model it. And what we're modeling there is essentially viscous dissipation. And you'll see that literally the energy just dies after a certain point. And you're down there at what's called the Kolmogorov scale, where the dissipation by viscosity is so fast, we do not have smaller and smaller eddies. They literally disappear. And it's at that region that we've taken all that kinetic energy out. So in order to do modeling here, we have to specify this subgrid scale model to dissipate energy. And that's not such a big task. There's lots of models, but long as you get rid of the energy there in a meaningful way, that'll work. Where the real difficulty comes is the wall treatment. So if we do just straight LES, we've got to resolve all the scales down to the wall. So all the way down to that grid limit, we've got to go to the wall. And if we say we're resolving down the wall, that grid limit has to keep moving right the further we want to resolve. So another option is to use a wall function. And then we know that in the early days of RANS modeling, that was really the only choice we had. We would use a log layer near the wall. But that immediately makes some assumptions about the turbulence there. So let's have a look at what's going on in there. So why is there a problem? Let's have a look at here. We've got a boundary layer. So the horizontal surface is a flat plate here, and we've got a low Reynolds number and a high Reynolds number. So as our Reynolds number increases, this viscous layer where all the damping's occurring is getting smaller and smaller. Typically, our large scale eddies stay about the same because they come from the size of the geometry. But what happens is that as we go up in Reynolds number, we need to resolve more and more of this. So you can see we need a finer and finer mesh. So that's the problem. We've got a starting point of large eddies, but as we go down into this box, these are getting smaller and smaller. So the thickness goes down here, and we have more and more energy here in these eddies that we need to resolve. So it's really a very strong scaling if we're going to resolve it at a wall. Now, other applications where you've got like a jet in a flow, you don't have much importance of the walls, and large eddy simulation is super easy there. It's really when you've got any sort of wall that the difficulties arise. So let's have a think now about how we're going to do this. So let's stay with this situation where we've got a certain thickness here. And how could we get around that? Well, we've got a couple of options. We've decided we're only going to resolve the yellow eddies, the yellow scales here, and everything beneath that we're going to get rid of. So then we've got a couple of options. So if we take the log law approach, we have a certain cell size here, and we say that we've got a logarithmic profile at a certain height there. And that's just like you might do in, say, a K-epsilon model, where we put that first cell needs great care, because if we put it too close to the wall, it's unphysical. If we put it too far away from the wall, it's unphysical. And we're not really resolving things then. And now we've also lost our ability to do things like separation properly if we're using a log law, because that'll tend to keep the flow attached if we've got a curved boundary. So the other option is to do modeling in here. And so we know from all the derivation of the RANS models that where they're really good is in the boundary layer, especially the SST model, which has been tuned for that. So SST is going to do a really good job. If it comes to an adverse pressure gradient, it's going to want to separate, and it's been tuned to do that, where the log law will just carry on sticking the flow to the wall. So we can see there's a big advantage, if we could, of using an appropriate model in the two different domains. So if we do a wall modeled concept here, and the early stuff did this via an algebraic model, what we could say is that close to the wall, we could take the eddy viscosity or the turbulent viscosity here and take some sort of value from RANS, some sort of value from the LES, and take the minimum of that. And that RANS model could simply be a mixing length model or something very, very simple there. And often it's then gone on to be supplemented by transport equations. And I guess the big one to start this off was detached eddy simulation. And now stress blended eddy simulation is definitely our recommended way to go. And I'll show you why in a slide. So that's really saying, let's take the best model and apply it in each region. So we've got plenty of these algebraic models sitting in CFX and Fluent, and we've also got the SBES model available now. So just a little bit of background before I move to the next one, next slide. Just to say that because of resolution constraints, so things like these channel flows have been examined with direct numerical simulation, and so grid requirements for LES can be rigorously established by comparing with those results, set some guidelines as to how fine the mesh must be. Now, not just normal to the wall, but along the wall and across the wall. We can't do anything in 2D in LES, okay? So we've got to have enough resolution across to build all these structures. So all I want to show you here is that if you choose a Reynolds number based essentially on the friction velocity here, then as this starts to go up a bit, the requirement of cell size, number of cells to integrate to the wall, explodes and becomes completely and totally impractical. So you can see immediately why we just don't recommend this. And the big issue is a lot of people using LES don't realize this. And you ask them a question, you say, did you resolve that to the wall? And they say, oh yeah, it's completely resolved, it's LES. And then they tell you they're using 1 million cells and they've got a Reynolds number that's 10 to the 5. So you just know that it's actually not doing what they say. Something's kicked in the code and you're using a log law, and that may or may not be appropriate. So let's see what the formulation is. So what the formulation says is, let's blend these models at the stress level. So we've got a closure stress for RANS, we've got a subgrid scale stress for LES, and we can blend them together. And obviously at the two limits of 0 and 1, we recover a pure model. But if we then think about this as an eddy viscosity type model, then we can get rid of the stress and replace that by a viscosity. And so this is our turbulent viscosity. this is our subgrid scale. Viscous term, essentially the damping there, that's representing that damping effect. But we don't change anything else. We don't change anything in RANS. We don't change anything in LES. And we just blend them together. So we can combine any RANS model with any LES model we want. So we can choose our RANS model to give us good behavior near the walls, and we can choose our LES model that's our favorite subgrid closure. So all the complexity is in this blending function. Now, I can't tell you the full details of that because this is proprietary to ANSYS, and that's where this model is really the basis of it. Is out there. It's the whole basis is clearly defined here, but the devil is in the detail to make it work. Now, how do we know when something's working well here? So we've got a flow here across like a backward facing step, and we're going to look at the results for 2 million cells and 7.5 million cells here. And what we want to see here is what's going on. So the first thing to note is this detached eddy simulation has not tripped into scale resolving mode. It starts to do it here. This is very typical of what you see in a URANS model. So you basically have these perfect cylinders with a size that's determined by some feature of the geometry, not necessarily physical, because of the way the source terms are written in the code and were designed. If we take this same flow in, so these two have got the same mesh, then you can see that very quickly that transition starts off like this, but here it's broken up super quickly, and we've gone into scale resolving mode. So you get this much faster transition, and it transitions faster on a coarser mesh. And you see here that when we go to a finer mesh, this is still not transitioned, but this is transitioned, and now we're starting to resolve more of the structure. How do we know what's going on in one of these models? Well, you can actually plot the blending function. So red is RANS, blue is LES, and you can see here, this is our backward facing step. So really quickly, that's transitioned to full LES. And in these more stable regions here, it's taken a bit longer. This is only transitioning when that shear layer gets out to there. But the key point is it's transitioning right here. So you're now using the best of both worlds, because you're using the RANS model upstream here. You can do your LES here, and later on, if we have a coarse mesh near the exit, this could easily transition back to a RANS solution, which is good for passing out an outlet, because you won't have all these complex eddies trying to go out an outlet. You'll just have a much simpler flow. So this is essentially where we're at with these type of models, and SBES can be used for an enormous number of applications. We've got a couple coming up, but the sorts of other things, heat transfer when you've got complex behavior, sound, so noise prediction, you can get actual fluctuating pressures out of this, which are really good. It's really good for mixing. If we got reactions that depend on mixing, then we're going to get a much more sensible mixing profile out of this, so in combustion, than we are with something like this. So with that, I'm going to hand over to Gary. If you want more information on the work, and we'll post this, Gary's written a series of papers on this. I don't think it's any secret that Gary's doing a part-time PhD, which he's going to be submitting very